Recorded, rolling. Yeah, it's Monday, December 15th. So I have a few warm-up puzzles for you guys. We'll go through these. Just to get ready for this midterm. You guys remember midterm is 20% of your overall semester grade. That should be true for all your classes. Okay. So here's how you calculate your semester grade. Here's how you calculate what you need on midterm. Here's an example in PP. Do that. And then you should have one of these Flipbook diagrams, so we'll get to this after the practical. Here, I'll show you guys the midterm schedule also. So tomorrow, your only midterm tomorrow is period 1. And then all your other classes are shortened. And then each day after that, you have just a couple of classes that you go to. 2, 3, 4, 5, 6, 7. Well, tomorrow we get up 30, so not tomorrow. But yeah, each day after that. Yeah, Wednesday, Thursday, Friday, you get out at 2:30. Yeah. All right. So let's look at some warm-up puzzles. Warm-up puzzles here. I got a few of them. Start with that wood. Guys, calculate what's the acceleration. If this were on an exam, it might be phrased like, what's the downward acceleration of the large block, stuff like that. Okay. Go ahead and calculate acceleration.
Yeah.
Alright, here is the acceleration. Acceleration of this at wood. Huh? What? Okay, yeah, it has to do with Newton's second law of motion, F equals ma. Yeah. Guys, the F in F equals ma, that's like a net force. Here, how about this? Right, guys, these masses are fairly close to each other, right? 4 versus 5 kilograms. So on a spectrum from no acceleration at all to pure free fall, 10 meters per second squared, this is probably a lot closer to what? Closer to 1, you're saying?
Awesome.
Anybody writing on paper? That might be helpful.
Because I did.
Especially if you're not getting this right away, you might be good to take some extra notes. You guys think maybe I was peeking at the midterm this morning, shopping for questions I should be asking you guys right about now?
Yeah.
It's like I'm writing all of this down. It's like
Oh, 1.11? Yeah. All right. Thanks, Austin. Right, so way to do this is
because 5 newtons up.
Well,
5 newtons down.
there are two main methods you see for this. One is to set up a system of equations, look at this block in isolation, this block in isolation, and make a system. Okay. I normally don't do that with you guys. What I normally do is what's called a whole system approach. Okay. So, guys, what's this weight equal to? If this is 5 kilograms mass, this is approximately 50 newtons of weight because mg, right? If g is about 10 to your squared. And this 4 kilogram guy over here must weigh about 40 newtons. Right? Now, if the question had something to do with this string up here, maybe you consider like adding these together or some version of that. Okay. That's not what we're doing. We're looking at the motion of the two blocks. Like one's going down, one's going up. So I'm treating this like a tug of war. Guys, tug of war. If one guy pulls 50, and the other guy pulls 40, and they're competing against each other, then what's the net force they get into that framework? 10 newtons. Okay. So we're going to acceleration is net force on total mass. Right? There's Newton's second law of motion right there. Newton's second law. Okay. And the acceleration is, okay, you guys said take 50 minus 40 at newtons. And how much mass is being moved around?
4 plus 5.
9, yeah, 4 plus 5, so 5 kilograms plus 4 kilograms. Right. You guys know force is a vector, mass is a scalar. Okay, that's why the track versus that. Yeah, you should get about 1.11 meter per second squared out of that.
You didn't know.
Okay.
You guys don't like a.
Alright, you guys saw that one? Okay. There could be a whole host of follow-up questions to this. Like what is the tension in the string? I would focus on one block or the other block. You know there how much it's accelerating now. You could get asked how fast does it move after some time, how far some time, how fast after some distance move. Those are all good kinematic follow-up questions.
That's it.
There's that last one you can probably talk creative energy.
Say that.
Alright, that would alright, how about I got a block on an incline. Guys, let's say there's no friction. There's no friction. You guys got that? What is the acceleration of that block down that incline with no friction?
Oh.
I got a 15-degree angle. 15 degrees. What's the acceleration? Say we're on Earth. Alright, I got a number on my calculator screen.
Okay, what are we doing?
Guys, there's no friction on this incline. What's the acceleration of this block going down the incline?
15. 15 degrees.
15 degrees.
Is it like 9.9?
Here, guys, 15 degrees from the horizontal. That's fairly shallow, right? Do you think so? On a spectrum from no acceleration at all to pure free fall 10 meters per second squared, this is probably closer to what? Probably closer to zero. Now, of course, it is accelerating. There is some acceleration, but from 0 to 10, it's probably closer to 0, right?
Doing the same thing.
From 0 to 10.
It's not. Technically, that was the way. Technically, this is the right answer. Do that.
I think what I would do is create a free body diagram and start working it from there. Oh, I never gave you the mass of the block. Guys, does the mass of the block matter or does it end up canceling out? Cancel out. Okay. So you know 15 degrees right here. Okay. Did you guys throw a weight acting straight down? Call it MG. Okay. Okay. What next? Are you guys trying this out with me? You guys writing this down? Yeah. This is a really classic puzzle, okay? And students mess up all the time on how to draw this free body diagram. Okay. So the weight's pulling straight down. There's what other force on it? A normal force. And normal, guys, does normal mean straight up?
No.
Perpendicular to the surface. Isn't that like this direction? Okay. But how long should I draw that normal force?
Same as the same.
You understand what we're doing that, right?
Is this the same as MG, longer than MG, or shorter than MG? In this context, it is shorter. Okay? Okay. Now, if it was a horizontal surface, so you can call it the same as MG. If it was a car on a banked road going around, it would be more than MG. But this context, sliding down would be a little less. Right? Well, how much exactly a little less? Well, maybe what I should do is I should break this weight into components that are perpendicular to the surface and parallel to the surface, like this. Okay? That, guys, this weight is partially pushing the block into the surface and partially trying to make it accelerate along the surface, which is what we're really interested in, isn't it? Okay. So I think this normal force right here, what you guys mentioned, has to balance out this component of the weight, doesn't it?
Yeah.
See? Right. What is this angle right here? 15 degrees. 15 degrees. Right. It's always going to match this one. Okay. So this component must be mg times what? Mg cosine theta. Okay. Which is equal to the normal force. So normal force is mg cosine theta. Okay. Right. But we're actually way more interested in this one right here. Yeah. This is mg sine theta. Right. And isn't this right here the net force on the block? Because everything else cancels out. Right? The full weight I broke into components. So I'm thinking about the weight in terms of those two dash components. Okay? The normal force canceled out with the cosine component. All we're left with is mg sine theta. That's the only thing left standing. So that has to be the net force. So same as we did with the output, we're going to go through Newton's second law. Let's go. Acceleration is net force on mass. Right? And the net force in this case is mg sine theta. Mass block is in. So the acceleration for this scenario, again, if there's no friction, it's always the sine component of times the gravity field. Now if you pop in 10 meter per second squared here and 15 degrees here, you get 2.6 meters per second squared.
I totally get it.
You guys do inclines? Inclines?
Alright.
Alright, how about this one? I got a planet with a couple of satellites going on it. You guys see a couple of satellites? Now one satellite, you see it's just above the atmosphere. I'll call it some distance r. And one satellite, let's say it's way out there in space. Maybe it's geosynchronous, depends how fast the planet's spinning. It's like at 5R out. You guys see it's 5 times as far out. Now each of these satellites has some orbital speed, right? You have to give it some speed to keep it in a, let's say, a pretty well circular orbit. Right? So how fast is this one way out here compared to this one close? Right. Okay, so the one that's further out is going faster or slower to stay in orbit. Here, let's say this planet was Earth. Guys, this planet's Earth. How long does it take the International Space Station to go around? 90 minutes. Right. How long does it take the moon to go around? Yeah, a whole month. Whole month. Moon month. Let's start with MO. Moon month. Right? Right. Yeah, I think you're going slower the further out you are. Right? The gravity field's weaker. You don't have to go as fast to stay in orbit. Here. Maybe it's good to be able to derive this from scratch. Like, how do you calculate orbital speed? Can you guys derive it from scratch? Go ahead. Derive from scratch. Orbital speed. Orbital speed. It's on either one of these satellites. Is it the only proper force acting on it? A gravitational force pulling it straight towards the planet?
Yes.
Okay. And that gravitational force, what do you call it? GM over distance squared, something like that. Okay. Capital M, the mass of the planet, little m, the mass of the satellite. Okay. That's acting as the what kind of force? Centripetal. Aha. You guys, what's a good fraction for centripetal? MV squared over R. Okay. Where this m is the mass of the what? Satellite. Now can you solve for V? Yeah, this should look super familiar, shouldn't it? Have you seen this? Where it comes from? So you set centripetal force equal to gravitational force because the centripetal force was provided by the gravitational force and nothing else. Okay? It gives you the orbital speed for a circular orbit. Okay. Guys, now you know, universal gravity constant is the same everywhere. They're orbiting the same planet. That's the capital M. So that's all locked in place. But back to this picture, I put this far out satellite as 5 times as far away relative to the center of the planet. So if you throw a factor of 5 in that R, then what is its relative speed? Yeah, 1 over the square root of 5. Is that what you got? 1 over the square root of 5? Okay. And as a decimal, that would be about 0.45. Okay. So it's going less than half as fast. Less than half. Because isn't that what 0.45 is? A little less than half. Okay. So whatever speed is going.
Then we just add a number.
If you want to, you could throw some numbers in here. So you could say V or 2 compared to V or 1. B square root G M on 5R compared to square root G M on R. What goes away? 1 over the root 5. or about 0.45. You guys see that? All right. How about ooh, guys, what if you see a force versus time graph? What's the question probably going to be about? Impulse. An impulse is what property of that graph? Area under the curve. Okay. Now, if you did see a constant force like this, then what shape is that? Rectangle. So that rectangle would represent the impulse, which is a change in momentum, right? What if I change the graph a little bit? What if it was force versus distance? Now that would be a different kind of graph. Now the area under the curve would represent the what? The work, which is like energy units measured in joules, like a transfer of energy. Okay. All right, you guys good so far? Let's go back to this incline. I meant to ask you guys another question about this incline. So the question I asked you guys was a zero friction incline. What's the acceleration? Okay. And then I walked you guys through this, right?
Yeah.
Okay. Here's a harder question. What if this block is sliding down at constant velocity? What question am I about to ask? What's the coefficient of friction? Coefficient of friction. So, yeah, I'll walk you guys through this step by step because this one's a little tougher. But no, it's a really similar free body diagram. Guys, how is this free body diagram different than the one we did a couple minutes ago? Yeah, it has a friction force. It's like I didn't draw that before because before it was a frictionless incline, but now it has friction, allowing it to slide at constant velocity. Okay. It has to have friction. Okay. Right, so I'm saying there's zero acceleration, therefore there must be zero net force. Therefore, what do you think is next? Exactly. This friction force has to be equal to this mg sine theta component right here. Right? Okay, well, couple steps. So along the axis parallel to the surface, it has a zero out, therefore that would be true. Yeah. Right. Now, if the question is coefficient of friction, we've got to sub that in somehow. So how's that going to sub into this? Yeah, friction force. Isn't that coefficient of friction times the normal force? Right, something like that. There it is. Okay. All right. Now what? Yeah, guys, normal force is mg what? Mg cosine. Yeah. Guys remember that? Mg cosine? Okay. So normal force has to balance out this mg cosine component. Right? Okay. Yeah. Do you guys see a bunch of stuff about cancel? The M, the G. Right. There's a cosine theta here, there's a sine theta here, and here's your coefficient of friction that you're solving for. State coefficient of kinetic friction. So what's the last step?
Do you divide the empty cosine on both sides?
Okay, yeah, you do, and then the mg cancels. What's sine divided by cosine? And theta. Right. Yeah, you have an old lab paper where you guys did that. Did you guys? I figured some classes I think tipped up their desks, and some had the idea to. I know I had the aluminum inclines out, so you maybe use those.
Would it be 2.27?
Oh yeah, for 15 degrees.
Yeah.
Yeah, let's see, tangent 15 degrees. Let's see, yeah, 0.27 about. Yeah, looks like a pretty common reasonable coefficient for right. So you guys know midterm in this class it's going to be in two halves. There's going to be 50 conceptual questions, and we took about 3 days of Kahoots to go over those. Right, and that was the study guide I gave you guys. So 50 of those, about 100 or so questions to go. And then the second half of the term is going to be 10 puzzle questions. And there was a more recent Kahoot we did with 25 questions. Right, so I think if you study those and
Wait, are those on Google Classroom?
Yeah. Guys, on Google Classroom, I posted both the videos that we covered in class and also the Kahoot links that lives there too. Okay. All right.
Yeah, I did. Is that what's going to actually? They're all going to get it. No, the video is not
All right, Flipbook time. Hey, Okay, you guys got this foot. Okay. Now, right now, it doesn't really do a whole lot. Okay. But you guys got some heavy duty scissors. You guys got some. Now you might just share some scissors around. No, it's quite a heavy duty ones out there. Okay. So, do you guys see the staple binding on the left?
Yeah.
You guys know you're gonna flip it like this, right? Okay, but right. Well, unless you want to go all Japanese with it. Right, let's go with it. Alright, so guys, follow these steps. Take this staple binding right here, right, and roll it over once, twice. Guess he did once, twice. So that it looks like this. Looks like this. You're making a cinnamon roll. Right. Okay. If you got that, be tight. If you missed that, I'm gonna redo that step. Okay. Right, so you got the binding on the left side. I'm gonna roll it over once, twice. Right. Oh, it looks like that.
Okay.
Okay, so now yours looks like this. Okay. Now flatten this out over here. Okay. Now there's probably some you could kind of flip a little bit, but and then there's a bunch that's like that. Okay. Okay. I want to shave all this off. Right, so I'm gonna cut all this off, probably right about here. Right about here. Okay. Okay, make it goes real straight here.
Yeah. Wait, what? Not at all. What we shave off?
Like that. Okay. So that. Do you guys see how this is pretty well even right here, right? Okay. But when you unroll it, unroll. Ooh, look at this. Really nice flip books. Look at that.
Oh yeah, mine is too.
Right.
Like.
I got flip book. Okay. Got a bunch of past examples. Let's look at some of these. Right, so you get to apply some physics knowledge here. I want you guys to create a flip book of something in motion. I mean, that'd make an exciting flip book, right? So here, let's get this. Ooh, you guys see this ball bouncing? Ball bouncing? Now, if you want to make this a proper flip book where your brain kind of believes the story of what's going on, then do you think maybe it'd be good to apply some math and physics? Say, like, what should the height of the ball be as a function of time? Where every page flip maybe represents some equal increment of time. Right? So if it starts at the top, maybe it's gonna fall not too far during the first second, right? And then it falls. Ooh, look at this gap growth spreading out. Right now it's falling a lot. Okay. Then next frame, you guys see like the gap is spreading out. That really reminds me of that ball falling off the cliff coaster. You guys remember that too? Okay. There you go. Pull that up real fast. I think I find this real fast. It's there we go. Yeah, you guys remember this, right? Right. Got the ball spreading out. Ball spreading out. Okay, set. Yeah, that looks pretty realistic. Okay. Can you guys take this to 2 dimensions? Take it to 2 dimensions. So this has the same vertical motion as before, doesn't it? Where see it's going up fast to start with, right, and then it kind of slows down at the top, and then it comes down faster. Right, same thing with the kitty cat. But what about the horizontal motion? If you get it exactly right for a projectile, what should be happening to the horizontal motion? Yeah, it should be pretty well constant going across the page. It should be exactly right. Let's grab the spear.
Yeah. I usually start with the last
Yeah.
Yeah. You missed it.
Oh, this is the B.
What we got next?
B.
That's Tyler. Yeah, Tyler.
It's not a geometry, that's
Don't make money. What we got next?
Alright, so where do I put these?
A happy shark. He's just a hungry shark.
Hey, yeah.
Where do I put these? Where? That's cool. I make it like image one from the middle.
I think I want to do.
You make it.
No, it's not China's playing. George.
Oh, yeah, that's.
Light's kind of weird on this. Where's the?
It showed for a while.
Just that.
Just that.
Just can't.
Whoa. Whoa. So let's just.
Oh, we're making those.
Uh-oh.
Oh. Oh.
Oh.
It
missed. Oh, dude, I was gonna say.
Oh, yeah.
Solar system. I don't think what I want to do.
All right. I bet you guys can use your imagination, come up with some good flip books, and give you guys some points there.
Oh, wait, you just.